Good day everyone, I'm Theon Cruz and I'll be presenting water activity sensors for use in food safety application. At least once in our lives, we may have encountered food-related illnesses caused by microbes. In the worst cases, they could lead to death. According to a 2010 statistics by the World Health Organization about food-related deaths, 3 microbes already account for 35% of the total number. This is an alarming fact, which is why there is focus on food safety with regards to microbial contamination. A useful tool for understanding microbial growth in food is to correlate it with the food's water activity. Water activity is a measure of free water in the system. It is not the total water content, rather, it is the water that is available for use by the microbes. A graph here shows the reaction rate versus water activity, where the highest water activity is 1 for pure water. It can be noted that mold propagation can only occur at water activities of 0.6 or higher, yeast with 0.8 or higher, and bacteria with 0.9 or higher. Therefore, 0.6 water activity and above can be considered as the critical range for potential microbial contamination. It is an important concept because it can predict chemical and physical stability and type of microbial growth. To get water activity, you measure the vapor pressure exerted by the water in food over the vapor pressure exerted by pure water. But there is no such device that can measure the vapor pressure of water in the food. To determine water activity, we use water activity sensors, which indirectly compute for water activity by getting the equilibrium relative humidity. There are 2 ways. First is the capacitive sensor theory. By placing the food sample in a closed space and allow it to equilibrate in the air around, the humidity in the air can be correlated to the water activity with this equation. To determine the equilibrium relative humidity, a hygroscopic polymer attached to the circuit will pick up water molecules in the air and induce a change in electrical readings. Water adds to the dielectric constant between the capacitors, which allows the capacitor to store more energy between the plates. Given the provided standards with known water activity, the device can be calibrated. Problems arising while using this method are long equilibrium times for temperature and humidity. The second method is a chilled mirror theory where the dew point or saturation point is determined. The schematic is shown on the very right. After equilibration in a closed system, the mirror is cooled using a thermoelectric cooler and starts to collect water vapor on the surface. A light source is directed to the mirror and reflected off to be read by a photodetector. The mirror starts accumulating water droplets due to decrease in saturation of water in air by lowering the temperature. The water accumulation results in a decrease in reflected light intensity, which marks the dew point. Simultaneously, the food sample temperature and the surrounding temperature are recorded using infrared thermometers during the initial decrease of the reflectance reading. The difference in the two temperature readings corresponds to the relative humidity of the system, similar to how a regular hygrometer works, measuring hot and cold air temperature. The relative humidity can then be converted to water activity. These two methods are the conventional and standard ways on how to determine water activity. A study by Basak et al. Used the chilled mirror theory to build their water activity or humidity sensor. Instead of LED, they used fiber optics to increase detection sensitivity. Their study and many others focus on improving accuracy. The problem is, the pricing of the devices is relatively high such that the smaller industries will not be able to afford it. Water activity is a more informative correlation to microbial growth than water content, pH, and temperature. Thus, it will truly benefit to food safety, especially for the more dubious foods and their packaging. One possible way to build a cheaper sensor may be to integrate colorimetry, similar to litmus paper. Instead of reacting to acids and bases, the sensor should react to water. The main concern, however, may be the detection limit, as colorimetry might not be as sensitive as capacitance or resistance readings. But if it can read as low as 0.6 water activity, then it will serve its purpose. Finally, I'd like to show the patent by Decagon Devices for the earlier model of the dew point water activity meter. Their diagram indicates how the air is circulated and how water quickly evaporated back to vapor by using a heating fan. This allows equilibrium to be reached more quickly. With that, I end my talk. Thank you for listening and have a good day.